Hello, this is Mr. Stansbury. I'm going to take you through some of the problems on the 5D assignment. We're going to start here with number 1. A nest of ants initially contains 5,000 individuals. Population is increasing by 12% each week. How many ants will there be after 10, 20, so forth and so on? So what we want to do is we want to write ourselves a little population formula here. So let's do this. Population, P equals... Always start with your initial amount, so that's 500, and then we're going to multiply by 100%, so that's 1, right? 1.00 plus our increase, which is 12%, so that's 0.12, and that's going to be all to the t for time, or let's not do n, let's do t for time, and that's going to be time in weeks, right? So really it's going to be population equals 500 times 1.12 to the t, okay, which is really pretty similar to our geometric. This really is a geometric series here, but anyway. So we would simply write it like this, and then just to kind of double check it, if we put time in at 0, 1.12 to the 0 power is 1 times 500 is 500, which is what we're starting with. Okay, so to make these a lot easier, you want to come up with your population formula here. Okay, so now for A, how many ants will there be after 10 weeks? So to figure that out, we just do P equals 500 times 1.12 to the 10th power. Plug that into our calculator, see what we get, and away we go. So 500 times 1.12 to the 10th gives us 155.3 ants. So the population is going to be about 100, no, not 155. What did I do? That's not right. 50 times 1.12. Oh, because I did 50. It's supposed to be 500. 500 times a 1.12 to the 10th. That's better. Now I still did 50. 500. Now I'm looking at it 1.12 to the 10th. Now I know I have it right. There we go. 1,553, about 1,553 ants. About after 10 weeks. Okay, so after 20 weeks would be P equals 500 times 1.12 to the 20th power, right? Now, quick little trick on the graphing calculator here. If you go back and highlight your formula that you put in, push enter, it will let you go back and edit that. So instead of putting that all in, now I'm just going to turn that 10 into 20 because it's the same formula, different exponent, and we get 4823. So the population is about 4823 after 20 weeks. Okay? And then part B says how many weeks will it take for the population to reach 2,000? So we want to know when the population equals 2,000. So for B, we would do 2,000 equals 500 times 1.12 to the 10th power. Okay. Now, to make this easier, first thing we want to do is divide both sides by 500, right? And that gives us 1.12 to the 10th, and that's going to when does that equal 4? Okay. And really what this means over here, this 4, if we start with 500 and we want to get up to 2,000, that's 4 times the original population, right? That's what that 4 is standing for. So on your graphing calculator, we could go through and we could do logarithms on this, which would be pretty easy, but we can also do this with the graphing. So I'm going to kind of try to do a little bit of both here and clear that one out. And so first one we can just put in 4. Second one is 1.12 to the let's see, sorry, we don't want it to the, we want it to the 10th, we want that to the t, right? So that's our variable, sorry. So 1.12 to the x power. Graph both of those. Oops, this was our original, this was from an earlier problem. which it's going to work out because it's intersecting right here. Okay, so I'm just going to do second trace, which is calculate. And it will hopefully eventually, oh, it's still graphing. That's why I was thinking. So let's try that again. Second trace. We're going to find 5, the intersection. And it says we want it to be with this curve. Yeah, first thing I'm going to do is I'm just going to kind of move it over a little bit closer, so it doesn't have to think as much. So is this the first curve? Yes. Now it's going to jump up to the other red curve. So if you pull it back down, you can see that it's on the red curve. Enter. Yes. Guess. Enter. And it gives us 12.23 for time. So time is going to be 12.23 weeks about. Okay. So that's with the graphing calculator. Just really quick to show you this same thing with logarithms. This point right here, we have 4 equals 1.12 to the t. So if we're going to do logarithms, our shortcut on logarithms, instead of, well, you know what, let's not do the shortcut. Let's just make this make sense. I'll let you find the shortcut. Log 4 equals log 1.12, and now this t can come out front here, so it's really log 4 equals t times log 1.12. Divide both sides of log 1.12, and that will tell us what t is, and hopefully it's 12.23, but let's just double check. So we do, let's clear that out, get the rest of that jibber jabber out of there. We do log 4 equals, and then we do divide by log 1.12, and that gives us, look at that, 12.23. 12.23 weeks. Okay, so you can do it with the graphing calculator, or you can do it with logs. Nice thing about logarithms is you don't have to worry about ever changing your window to try to make sure that it fits in there. Logs will pretty much always work. I usually tend to lean this way, but if you want to do it with a graphing calculator, go for it. Okay. Next one to take a look at, number 4. An endangered species of marsupials has a population of 178. However, with successful breeding program, it's expected to increase by 32% each year. Find the expected population size after blah, 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 blah. So we want to write ourselves a population formula. Population equals, it originally is at 178, and then it's increasing by 32% each year. So that's going to be 1.32. 1 stands for the 100%, the original 178, plus the increase of 32% each year, all to the t power. Okay, so now once we have that, we can simply plug in 10 for t and 25 for t and see what we get. So for A part I, we get population equals 178, 1.32 to the 10th, and we simply plug that into our calculator and see what it gives us. 178 times 1.32 to the 10th, and we get 2858.6, so let's call that 2859. So the population is about 2859 after 10 years. And then for AII, population will equal 178 times 1.32 to the 25th power. Okay, so nice thing about the graphing calculator, if I go back up and highlight the original one, push enter, I can go back and I can edit this one. So all I need to do is change that 10 to a 25. And that's a lot bigger. 183,979. 183,979. Oops, that's a 9, not a 2. About. So that's significantly bigger than the 178 that it started at. And then for part B, estimate how long it's going to take for the population to reach 10,000. Okay, so that's when we want to put plug 10,000 in for P. So we got 10,000 equals 178 times 1.32 to the T. Okay, I'm going to divide both sides by 178. And that's going to leave us with 1.32 to the T over here. And then on this side over here, we've got 10,000 divided by 178, and that gives us 56.18. Right? So so 10, that means it's 56.18 times as big as it was originally. That's a pretty big number, but you can plug that in the graphing calculator, or I'm going to do logs for log of both sides. I just find that to be less chance for error with this. So log 56.18 equals log 1.32 to the t, so that t comes out front, so it's log 56.18 equals t times log 1.32. Divide both sides by log of 1.32. And we get that t equals, so I'm going to take the log of that. It's already in there, so I'm going to do log second answer, so that it's not even rounded. 1.74 divided by log of 1.32. And that gives us, it's going to take about 14 and a half years, or 14 and a half, yep, 14 and a half years, okay, for the population to reach 10,000. Okay, one last problem to take a look at. Number 6, each year Maria's salary is increased by 2.3%. She began working for her company, she has been working for a company 10 years, and she currently earns 49,852 per annum, which is per year. Okay. What was Maria's salary when she joined the company? Okay, so now we're going to have to go backwards. So let's come up with our salary formula here. So her salary, let's do S equals, let's see, she's starting here at 49,852. And then it's increasing by 2.3% each year. So this is important. We got 100% plus 2.3% is 102.3, which means that this growth factor is going to be 1.023 to the t for time, which will be years. Okay, so that's her formula from where we're at right now. So she's been working for the company for 10 years. So we want to go back in time 10 years to see what she was making. So to figure out A, we would do her salary back 10 years ago would be 49,852, 1.023, and time is going to be -10. So to the -10th power. Okay. So when we plug that in, 49,852 times 1.023 to the -10th power. Super important to push this negative sign instead of the subtract sign. We push enter. That means 10 years ago she was making 39,712.41, right? 39,712.41. Yep. So our salary was 39,712.41 per year. Okay. And then for part B, if she stays with the company for another 4 years, what will her salary be? So that would be, salary is going to equal 49,852 times 1.023. Now she's going to go for 4 more years, so that's going to be to the 4th power because it's going to keep increasing by 2.3% every year. Okay, so now we can simply put that in. So I'm going to go back up to this, push enter, and I'm just going to edit my power to be 4 instead. So I'm going to delete those and put 4 in there and push enter, and we get 54,599.05. 599.05 will be her salary in 4 years. Okay. All right, that's all we have for the 5D problems. If you have any questions on these or any other ones, please feel free to ask. Thanks.